going to do some more of these angled launch problems with you, for you, alongside of you. Not much room to do the work on here. Do it all on a separate sheet here. Baseball leaves bat at 76 meters per second at 57 degrees above horizontal. Let's make a little 57 degrees, so that's more than 45, maybe something like that. Here's my 76 meters per second. I'm going to have to break that into the sine and cosine components. 76 times the sine of 57. Let's draw my 57 in there. And 76 cosine 57. All right, and those are going to be this is my constant horizontal velocity, and this is my initial vertical. So I didn't even read exactly what I'm supposed to be doing here in this question. Well, I did at one point, but I know I'm going to have to do this, right? So I'm just going to get it all set up. And I know this is going to be negative 10. And I got my Vx, my constant horizontal velocity, and I've got my initial vertical velocity. All right, let's see what else we got. How long is it in the air, and what is the maximum height? So we're assuming here in baseball that the ball is pretty close to the ground when it starts, and then it's going to go up, and then it's going to come back to pretty close to the ground. Maybe somebody catches it, maybe they don't, but we're going to assume that we're like ground to ground. So that means that my delta y is 0. If you set this problem up and had everything in place but just didn't realize the delta y was 0, then you should pause now and see if you can finish it here. So for part A, I'm going to do delta y equals 1/2 at squared plus vit. That's 0 is equal to negative 5t squared, and then the vi. And you can do that with algebra pretty easily, or you can just graph it. Either way. You can do that off up to the side here. And around that to 12.7 seconds. And let's see, what else we need to do. So part B, what's the maximum height the ball reaches? There's a couple of ways to do that. The way that I'm going to show you is to do the max height, then my delta y is not 0 anymore. This is still negative 10, of course. The initial vertical velocity is still 63.7 meters per second. The final velocity when we reach max height is 0, because that's where it goes from going up, positive velocity, to down, negative velocity in the vertical direction. And I'd like to know what that delta y is. So that's my Vf squared equals Vi squared plus 2a delta y. So a little bit of algebra there. I'll call that 203 meters. All right. Number 2. Bullet fired at 677 meters per second, 30 degrees above horizontal. how long is it in the air, how far does it get before landing. So that's my time, and this is my delta x. All right, 30 degrees, something like that. And this is 677 meters per second. That's fast, but it is a bullet coming out of a gun, so there you go. I'm going to go ahead and break that up into 677 sine 30 and 677 cosine 30. So I'm going to call that, let's go 3 sig figs, so 339 and 586. 339 and 586. All right. In the vertical direction, this is my initial vertical velocity. Delta y, we're assuming, if it doesn't say anything about it's launched from whatever, then you just have to assume that it's a ground-to-ground, so same as the last problem. And my horizontal, got my Vx is 586, and I'm going to find the time over here, bring it over here, find the delta x, classic projectile motion problem. So to find that time, I'm going to do delta y is equal to 1/2 at squared plus vit. Delta y is 0. Oop, did not mean to put the units there. Put a t there. So you can graph, or since this is 0, you can do a little algebra for this one, if you like. So time is going to be 68 seconds. I think that's our answer for part A, right? And then for part B, once I know that, then the delta x is equal to Vx times time. So it goes about 39,800 meters. Now, if you're thinking to yourself, that's a lot. That is like not for real. Like that's 39 kilometers, or about 20-some miles. Would a bullet really go that fast, or that far, I should say? It would. It could most definitely go this fast. But when things go this fast, air resistance is a very big deal, even on something that's like aerodynamically shaped like a bullet. So that is not what would actually happen. If you did this like on the moon, for example, of course that would be different on the moon, but somewhere where there was no air for there to be resistance with, no atmosphere, then this is exactly what would happen. But air resistance is a very big deal when things are going that fast. All right, number 3. Football is thrown at a velocity off the top of a 150-meter tall building. So this time I got a delta y, negative delta y. Here's my football. Going to be thrown at 35 degrees, 25 meters per second. Go ahead and get those 25 sine 35 and 25 cosine 35. So go 2 sig figs on this one, 14 and 4.1. In the vertical direction, I got my acceleration. Initial vertical velocity is 4.1. The VF, don't know. Delta Y is, this is 150 meters tall, and it's going down. The football is going from here to here, so got to watch out. A lot of the time our delta Y's are negative, so be on your toes. Make sure you don't miss that. VX is 14 meters per second, and delta X T. So I'm going to find how long will it be in the air before it hits the ground. So that's my delta Y equals 1/2 AT squared plus VIT. Going to have to graph this one because I've got my minus 150 here. So minus 5t squared, and then I've got plus 4.1 t, and then add the 150 to the other side. And if you're reusing like I am, just make sure you delete anything that's left over at the end. And I think my window should be good, right? I've got my 0 to 10 and my negative 10 to 10, so that all looks good. And there it is, somewhere between 0 and 10, right? Second, calculate. I'm going to find that 0. Oops. Not sure what happened there. Try that again. Calculate. There we go. Left bound 0. Right bound 10. Guess 5.9 seconds. And part B, how far will the base of the building will the ball land? Sorry about that. How far from? I know how to English sometimes. How far from the base of the building will the ball land? That's what that's supposed to say. Delta X is equal to Vx times T. Vx is 14. T is 5.9. That's about, I'm going 2 sig figs in this one, so I'll call that 83 meters. Alright, that's the first 3 done. Suppose a softball is thrown at an angle of 32 degrees above the horizontal at a speed of 19 meters per second. The softball is caught at the same height it was thrown, so that means our delta Y is going to be 0 again. So let's see, it's thrown 32 degrees at 19 meters per second. So 19 times the sine of 32 and 19 times the cosine of 32. So let's see, how are we going sig figs here? How about 2? So that's going to be 10 and 16. It's my VI. Alright, and in the horizontal direction, my Vx is 16. What's the maximum height reached by the ball during its flight? So for part A, that max height is when this is 0 and this is not 0. So I need to just redo that real quick. For max height, I'm always going to set the Vf equal to 0, because that's when max height happens, and then I'm going to find the delta Y. And that's always going to be my Vf half squared equals vi squared plus 2a delta y. So that looks like it's going to be 5. $5 is the max height. Okay. What's the velocity, speed, and direction of the ball at its maximum height? Well, that's just kind of a thinking question. If you think about what a motion map would look like, we have the path of the ball is like this. I guess there's different ways to think about this. At the very peak, when the ball is at its maximum height, what's its vertical velocity? Well, its vertical velocity is 0, right? Because it's not going up anymore, and it's just going to start coming down. But right at the very peak, all of its velocity is this way. It's all Vx without any Vi, or Vf, or vertical velocity. So that's 16 meters per second because the horizontal velocity is constant. So at the very peak, it doesn't have any up and down. It only has this. So it's 16 meters per second this way. And I'm representing that with an arrow. You could write that it's all horizontal motion at that point. What is the acceleration of the ball at the maximum height? Well, the acceleration of the ball is the same all the time. The acceleration of the ball is -10 meters per second squared. This does not mean it's going that way. This is the acceleration. This is how the velocity is changing. The velocity is changing this way. Notice that none of the acceleration is in this direction, and that's why the horizontal velocity stays constant. So what's the acceleration? It's -10, straight down, just like it always is. It is that all throughout the flight. That never changes. How long is the ball in the air for? So now I'm back to here, and my delta y equals 1/2 at squared plus vit, and this is the option play, algebra, or graphing. Either way, you're going to get 2 seconds. Is how long? How far does the ball travel horizontally before being caught? Oh, this is E. Well, I just need to do this over here. And my Vx is 16. My time is 2, so 32 meters. And finally, part F. What's the velocity, speed, and direction of the ball the instant before it's caught? Okay, so I need to do here, when it's caught, the horizontal part of its velocity is 16 meters per second, because that's constant. What would the vertical part be? Well, the vertical part is whatever the vertical velocity is after 2 seconds. So to find that, I'm going to use Vf equals At plus Vi, because I know the time now. So Vf is equal to -10 times the time is 2 plus the Vi in the vertical direction is 10. So that means my Vf is -10 meters per second. So here, that's -10. And if you notice here, these triangles, you can do like the trigonometry, do like tangent inverse of this over this, and the Pythagorean theorem to get this. But it's the same triangle as this, right? It's just kind of flipped over. So however you get there, the final velocity is 19 meters per second at 32 degrees below horizontal. When it got thrown, it was 32 degrees above horizontal, and then it follows that nice symmetric parabolic path and ends up with a final velocity of 19 meters per second below horizontal. When I say final velocity, I don't mean final vertical velocity, I mean total final velocity. All right, number 5. Golf ball is hit at an angle of 65 degrees above the horizontal. That's a pretty steep angle to hit a golf ball at. With a speed of 22 meters per second. And it lands on a green that's 5 meters above. That means I'm going to have a positive delta y. Find my components here. 22 times the sine of 65. 22 times the cosine of 65. And looks like I have 2 sig figs in this, so I'll stick with that. I'm going to call that 20 and 9.3. So in the vertical direction, got an acceleration of negative 10 meters per second squared. Sorry, my negative sign right there. The VI in the vertical direction is 20. The VF, don't know. The delta Y, this one is going up. It's going up 5 meters. And probably going to find the time in a second. 9.3. All right. How long is the ball in the air for? Saw that coming. Delta y equals 1/2 at squared plus vit. I think this is going to be a graphing one, right? Because I got a number here, 5. Negative 5t squared plus 20t. So there's my negative 5x squared and then plus 20x minus 5. Delete any other garbage you got there. All right, I subtracted that 5 over there. And my window should be good. Okay, now this is interesting. It crosses 2 times. So which one of those is the one that we're looking for? Well, if you look at the picture, you kind of imagine the picture of the golf ball doing this. It's going to be at that 5 meter height 2 times. On the way up and on the way down. Which one are we looking for? We're looking for this one, the second one. This is like that water balloon hitting the building problem. So when I look at this graph here, I'm seeing both of those times, and I want this one. So what am I going to tell the calculator? Well, I don't want to say 0. Well, we could try if I just go second calculate, find the zeros, and I do 0 to 10. See which one it finds. Oh, it found the right one. So you can try that. If it doesn't, if it finds the wrong one, then you just have to adjust your minimum and maximum and say, well, look from like 2 to 10 or whatever. So about 3.7 seconds. That's my answer for part A. And part B, what's the horizontal distance? It's called dx in this problem here. So that's the same as delta x, of course. So find the delta x. That's equal to vx times time. The vx is 9.3. And the time is 3.7. About 34 meters, rounded to 2 significant digits. And what's the velocity, speed, and direction of the ball when it lands? So that's a little trickier to find. That's like what we were talking about here. I need to figure out what the final velocity is after 3.7 seconds in the vertical direction. Because to do this, part C, I know that the horizontal velocity is still 9.3. And I know that this is going to be going down, but I don't know how much. And that's the final velocity after 3.7 seconds. So the final velocity is -10 times time plus the initial velocity. Sorry, I'm setting a bad example. Should always write down the equation you're using before you use it. Initial velocity is 20. So that's going to be 37, -37 is -17, blah, blah, blah. All right? So the negative just means it's going down, which we knew. We expected that. So what's the final velocity, magnitude, and direction? You have to do the same old trick that we learned how to do when we did vector review stuff. Going to have to do the Pythagorean theorem to figure out what the magnitude of that is. That's the square root of 9.3 squared plus 17 squared. Do not mess with that negative sign in here. Come on, you know it's going to go away when you square it, so you're only just asking for trouble. So that's about 19. I'm going to round it to that since I'm doing 2 sig figs in this problem. And then what's this angle? That angle is tangent inverse rise over run, tangent inverse y over x. And same thing, going to ditch the negative sign. Tangent inverse 17 over 9.3. That's about 61 degrees. So I'm going to answer for part C. The final velocity of this thing is 19 meters per second at 61 degrees below horizontal. And did not have enough room on the paper for the last one. A rock is thrown from level ground so that it's in the air for 4.3 seconds and lands 36 meters from its starting point. How fast and at what angle was the rock launched? So this is a little different just because of the information that we're given. We're kind of working backwards to get to that launch speed and angle, which is usually what we start with. So let's go ahead and set it up and see what we can do. Not really any harder, this problem. I guess it's only harder because it's less familiar. All right, so let's see what we got. It's thrown from level ground, so that's we're doing a ground to ground. Delta y is 0. It's in the air for 4.3 seconds. And it lands 36 meters from its starting point. That's delta x. Right? 36 meters, that could only be displacement, so it's either delta x or delta y, and if it's going from ground to ground, that's 0, and this is that horizontal distance. So I'm going to go ahead and do this first. I know that delta x is equal to Vx times time, so the delta x I can find the Vx from doing that. 36 divided by 4.3. About 8.4 meters per second. And over here, with this information, I can find the VI. So that's 0. I know what the T is, 4.3. Right, so a little bit of algebra here. Should get you that the VI is 22. Oops, didn't want to have that 0 there. VI is 22 meters per second. Okay, now what are we being asked for? We're being asked for how fast and at what angle was the rock launched. So if you think about where we start most of these problems, we start with some kind of little triangle where I've got the velocity, and then I break it up into the two parts. Well, this time I've got the two parts. So here, that's my VI, my initial vertical velocity, and this is my horizontal constant velocity. And we have those two. Sorry, came up a little short there. And I want to find the angle, and I want to find how fast it was launched at. So same as the last problem where I just need to do the Pythagorean theorem to find the launch speed. Be 24, rounded to 2 sig figs. And then to find the angle, I need to do tangent inverse, rise over run, y over x. Is 69 degrees. There you go.